Thanks for being here, and I'd like to thank the organizers for inviting me to this lovely conference. It's been very stimulating, lots of great ideas running around, and it's my first time in Turkey. It's absolutely lovely, so thank you for the invitation. My theory collaborators are Karin Dahmen at University of Illinois, as well as some of my PhD students. This is now Dr. Ben Philibam, and current students Forrest Simmons and Shuo Liu. Our experimental collaborators include Eric Hudson at Penn State and Jennifer Hoffman at Harvard University, as well as some of her group members, Conley Song and Liz Main. Our funders include the National Science Foundation, Department of Energy, Department of Education, Research Corporation, and actually Department of Defense I did not yet add. So the ways that we classify phases of matter, I mean, of course, we heard a talk in the earlier session about how we have a zoo of phases. We have to figure out how to understand them. So we have a couple of big tools for this. One of our big tools is symmetry, and this is where we're looking at the symmetry of the phase and how the symmetry changes as you go from one phase to another. So that's a symmetry classification. One of the things we have to keep in mind is that the symmetry classification of phases of matter is a long distance and long time criterion. So for example, one of the differences between crystal and liquid would be their symmetries, and the crystal breaks not just the rotational symmetry of free space, but also the translational symmetry of free space. The liquid does not, but that's only on long time scales and on long length scales. If you observe the liquid on short time scales, it's very bumpy, right? And if you observe it on short length scales, it's very bumpy. It's only when you take, say the time-lapse photography of this that it becomes smooth, and now it retains all the symmetries of free space. So the symmetry distinction includes implicitly long distance and long time criteria. Topology is another way that we categorize things, and these are simply objects with different topologies to them, different numbers of holes in them. And there's an implicit criterion in here as well of a long distance criterion, because you need some sort of edge or a boundary condition in order to define the topology. And so these, of course, have gotten us a lot of mileage. However, we're running up against things in quantum materials that challenge those paradigms. And the paradigms, we need new ways to think about phases of matter in systems that do this sort of thing. Now, we have many fascinating and a growing number of spatially resolved probes, and this has been excellent. And what they've shown us is a lot of pattern formation. So this is just a collection of examples of pattern formation happening to the electronic degrees of freedom in quantum materials. The two on the left are metal insulator transition materials. This is vanadium dioxide. This is neodymium nickelate. And the metal insulator patterns are being visualized using scanning near-field optical microscopy out of Dmitry Bazov's group. And so the different colors just tell you metal and insulator patches. And you can see there's a lot of intermediate scale structure here. And there's mesoscale structure that's missed by the definition of a phase of matter, whether it's by topology or whether it's by symmetry. The symmetry definition is blind to this because it's going to ask you about the long distance correlation properties. In the upper two panels, we have cuprate superconductors visualized by scanning tunneling microscopy. This is data out of Seamus Davis's group. This is data out of Jennifer Hoffman's group, and I'll show you the detailed analysis of this upper right one in this talk. And what's visualized here is stripe orientations. So the electrons make some sort of local charge density wave, and then what's visualized here is the direction that that wave goes in, one way or the other. And you can see that there's structure on multiple length scales here. This is another metal insulator transition material, V2O3, visualized with photoemission spectroscopy. This is strontium iridate, scanning tunneling microscopy out of Milan Allen's group at Leiden, visualizing Mott versus pseudogap. But the theme here is that there's a lot of different instances where quantum materials show interesting pattern formation and textures in the electronic degrees of freedom, kinds of things that are missed by the typical definitions of a phase of matter. So we need new ways to think about these things. And I'd like to remind us of something that happens at a continuous phase transition. So at a continuous phase transition, we get some very interesting phenomena that I think is related to what we're seeing. So this in the test tube is a video that is playing of, we have a mixture here in the test tube at high temperature. It doesn't actually matter what the mixtures are because the unmixing transition has universal properties. So two liquids mixed together, I think it's cyclohexane and methanol. And then as they lower the temperature, they're going to unmix. So you'll watch the unmixing transition, and you'll watch as they lower the temperature, the heavier liquid will gather here in the bottom, but first we're going to see critical behaviors. So you see these fluctuations starting at the top. That's the beginning of criticality. And you see these white tendrils coming down. And as we get closer and closer to the transition, the white tendrils are overtaking more and more of the test tube until finally those white tendrils overtake the entire size of the system. This is critical opalescence now, where you've got fluctuations on all length scales. Because you have fluctuations of the density on all length scales, you're scattering all wavelengths of light, and so it turns white. That's critical opalescence. And if we let the temperature go down a little bit more, you start to see the dense liquid is starting to gather at the bottom. Now, what's lovely about this particular demonstration is that you can see the correlation length. So right at a critical point, right at the second order phase transition, the correlation length goes to infinity, and all properties of the system take on power law characteristics. And so, for example, the density has fluctuations on all length scales. If you're a little bit away from the critical point, now the correlation length is finite. You still get critical fluctuations, but they only happen within a correlation volume. So when you observe the system on length scales smaller than the correlation length, you still see the critical behavior. Okay, and you can see that lovely visualization here. This is a critical fluctuation everywhere where it's white, and so you can see the correlation length is as long as the white tendril. And when we were a little bit farther away from criticality, right when those white tendrils started, you can see the correlation length there starting off small and then growing and growing and growing as the fluctuations, as the correlation length increases, and then it finally overtakes the entire system. So what's lovely here is that everything goes power law. And if we could take a zoom in and a zoom in of the density in the critical areas, we would see that because it's power law, it's self-similar. It looks the same on different length scales as you zoom in, which means there's a fractal nature to it. It's a disordered fractal, but it's fractal in nature. And when you have this second order behavior, there's universality. So there's universal power law behavior in the sense that all mixtures share universal features at their critical point, such as the critical exponents. So what does that have to do with this pattern formation? This pattern formation actually has structure on multiple length scales. And I'll show you how to see that there's actually a power law hiding in there. And we'll analyze it from the perspective of critical phenomena and see what kind of progress we can make there. So this is a visualization of scanning tunneling microscopy out of Jennifer Hoffman's group. This is BSCCO 2201, so a single layer BSCCO. It's an underdoped sample with transition temperature 32 Kelvin. The data is taken at 6 Kelvin, so low temperature. This is a 65 nanometer by 65 nanometer field of view. And what Jenny's group has done is in a local region, they take a Fourier transform of the R map. The R map is where you take the current at 1 voltage and divide by the current at the negative voltage. So for example, this one is current at 100 millivolts divided by current at minus 100 millivolts. One advantage to that is that the matrix elements cancel out there. And so it's a nice way to highlight changes in local electronic structure. And so they take a local Fourier transform in any given region of space. They see structure. This is the Bragg peak of where the copper atoms sit. And then there are these satellite peaks that can come up that indicate local charge density order. And they're in two different orientations. So here, if they're along this diagonal, then we color them red. If they're along this diagonal, we color them blue. So for example, in this region, where the stripes are running diagonally to the right, the wave vector appears here. And so we color those regions blue. If the stripes are in the other orientation, diagonally to the left, we color the regions red. So this is a map coloring the orientation of the stripes in this system. And so now if we think about what's going on with the spatial structure here, there's actually a lot of texture in here. I can actually, this big green line that I drew shows you one large system spanning cluster. So this red cluster, actually, you can walk from one side of this sample of this field of view to the other by making nearest neighbor steps onto red pixels. And so there's one large connected cluster. There are several medium clusters. I've highlighted those in yellow here. So the blue clusters are medium scale clusters. And there are many more tiny clusters. So I've circled some of the red clusters that are tiny. And so already you can see a hint that there could be power law behavior in there because you have structure over multiple length scales and you have a small number of large objects but a large number of small objects. So in fact, there is a power law distribution here. And I'll argue that it indicates proximity to a critical point, that critical behavior is driving this pattern formation. And if critical behavior is driving that pattern formation, we can get critical exponents out of it. Now, to discuss critical exponents, I need a model. So in this case, we have that the stripes are in one orientation or the other. An either or variable you can model with an Ising variable. So I'll call stripes that are diagonally to the right, sigma equals +1. Stripes that are diagonally to the left, sigma equals -1. We make the reasonable ansatz that neighboring stripe patches want to be aligned. So that's a ferromagnetic interaction. We allow that interaction to be in the plane, of course. It's a layered system, so there should be interactions within the plane. Because of the layering, the interactions are weaker between planes, so that's why I pulled off this interlayer coupling. That allows us to change that parameter from all the way from a 2D system. Maybe the interlayer coupling isn't important, and maybe we should just think about 2D correlations here, all the way to a fully three-dimensional system. Now, how should we model disorder in this system? So we model disorder here using a random field term, and here's why. So the interesting stuff is happening here as a function of doping. And here, doping is chemical substitution. It's uncontrolled, and so it gives you disorder patterns. And so you can imagine that in any given region of space, there's a pattern of disorder of dopant atoms, and their particular pattern breaks the rotational symmetry of the host crystal. So in one region of space, that disorder, those dopants would tend to drag the stripes in one direction, and somewhere else they'll tend to drag them in another direction. That's why it couples linearly to the order parameter as a random field term. There are other ways that disorder can come in. You can ask me at the end of the talk, but the other ways are irrelevant in the renormalization group sense. It's a simple phase diagram. You're either in the ordered phase or the disordered phase, and the transition out of it is always second order, always critical. And so then what we're looking for here is the different critical points. What are the controlling critical points? So the blue arrows on every phase transition line tell you which way you need to look for the fixed point that's controlling the critical behavior of that line. And so we have a few different fixed points here. We can be in the two-dimensional limit or in the three-dimensional limit. We could be in a limit where disorder doesn't matter for the pattern formation, or we could be in a limit where disorder matters. Or we could be, maybe things don't interact at all. Maybe this pattern formation is just a flip of a coin at every region of space on the surface of the sample. Maybe it's not interacting. So we include these 5 fixed points in our analysis. So if this pattern formation is due to proximity to a critical point, then I claim that critical exponents are encoded in this pattern. We just have to learn how to get them out. We're used to deriving critical exponents out of experiment by a sweep of some parameter. So for example, we might measure magnetization versus a sweep of temperature and get one critical exponent, or versus a sweep in external magnetic field and get another exponent. Here, you don't have to sweep anything. In a sense, the sweep has already been done as a sweep in position. So there's enough information in here, I claim, to get critical exponents out. So what can we get out? We can get out the whole fractal dimension. So this is the question of these boundaries. How lacy are these boundaries? And when we analyze that, we would be looking at the radius of gyration of a cluster versus its perimeter. When plotted on a log-log scale, it's nicely linear. This is out of the data. And so we have more than two decades of scaling, so we're confident in our ability to extract this critical exponent. I'll show you in a few slides what number it is on a chart. We can also get out the volume fractal dimension. So here we plot the radius of gyration of the cluster versus its volume. This is the question of how Swiss cheesy is the cluster. Are there holes in it? Are there holes inside those holes? That kind of question. And the volume is measured by how many pixels does this cluster cover in the image. We also take a histogram of cluster sizes, similar to the analysis done here by Bianconi's group. So here you would look at the number of clusters that are a particular size. We've analyzed here actually the moments of the cluster size distribution, but it's the same idea. You count how many clusters are of a particular size. This is also nicely power law. And then you can look at correlation functions. And these turned out to be a bit of a mystery to us. I'll tell you the mystery. You would expect, we all expect the spin-spin correlation function to go power law at these critical points. And the spin-spin correlation function is simply these two spins a certain distance apart. Are they aligned or are they anti-aligned? Okay, that's the spin-spin correlation function. And when Jennifer Hoffman's group plotted that in this data set, it plummets. This is a log-log plot. If it were power law, it should be linear. It just plummets. It's basically an exponential decay. So that was troubling to me. But then Jenny's postdoc, Les Main, had the stroke of genius to plot the paraconductivity function. So this is a measure from percolation theory. It's to track the order parameter from percolation theory. So the paraconductivity function asks the following question. These two spins that are aligned, are they in the same connected cluster? So if the spins are aligned, can I walk by nearest neighbor steps on same color pixels all the way to that other spot? So it's a question of connectivity. And this turned out to be power law. However, it's not a percolation exponent. So this exponent that comes out of the analysis is not percolation. And it turns out that, in fact, people hadn't studied this correlation function for the Ising model. So the paraconductivity correlation function, it turns out we calculated it in several different Ising models, and it also goes power law. It was actually already known from the 70s that it goes power law in the 2D clean Ising model, but we showed that it goes power law in the 2D random field Ising model and on free surfaces and on slices of the 3D models. So it's also critical in those. Sorry, it's also power law at all those Ising exponents. And I'll skip that analysis because of time constraints. So let me walk you through what these charts are. The horizontal lines are the exponents that we extracted from the data set on BSCCO. And then the width of that line is the error bar. Okay? And then the circles are theoretical calculations of those exponents. And so here we have the Fisher exponent, which is about the cluster size distribution. Here we have the paraconductivity correlation function exponent, the one I said is also power law at Ising models. We have the volume fractal dimension here and the Hall fractal dimension here. And then it's we figure out which ones are closest to the experiment. The left two columns are about the clean Ising model, whether 2 dimensions or 3 dimensions. The middle column is about percolation physics, so this would be just non-interacting. Because it's non-interacting, you only consider the 2-dimensional case because the observation of the STM is on a surface. And in the last two columns, we have the random field Ising models, whether 2 dimensions or 3 dimensions. And you can see, for example, that as is the usual case, critical exponents are sensitive to dimension. Here as well, in the clean Ising model, this critical exponent is sensitive to dimension. So what kind of inferences can we make based on this? Based on the paraconductivity exponent, we can rule out the clean Ising model in 2 dimensions. So this exponent is not matching. I know they look close on the graph, but this is the 0 line. And so this is about 0.2, and this is, this is about 0.1, and this is about 0.26. And so they're outside the error bars of each other. So it's not matching a clean Ising model. It's also not matching percolation. And so this right here, the volume fractal dimension is actually pretty far off as well. The random field 2D Ising model is off as well. The Hall fractal dimension in that case is not matching. So we've ruled out a few models with this analysis. What's left is the 3D models, actually. So this analysis isn't enough to distinguish for us between the clean 3D Ising model or the random field 3D Ising model. So you can't tell from this. It's just the numbers are too close to tell whether the disorder is mattering for the pattern formation. But I am excited that we can rule out the 2D models. Okay? So that means the structures that they're seeing on the surface are coming from the bulk. And so this is, I'm particularly excited about this because critical exponents are sensitive to dimension. This is a general method for any surface probe that sees multiscale pattern behavior. If they're seeing critical behavior, if they do this critical exponent analysis, this gives a way for the surface probe data itself to diagnose the dimension of the phenomenon. Okay? And this is great. This has been a standard critique of surface probes, is that they're only measuring the surface. So, so here's my analogy for why this should work. You're used to diagnosing fractals out of windows. This happens to you sometimes. Sometimes you look out of a window and you see a tree, and that's fractal. But you know that tree fills space. You can just tell by looking at it, right? In your experience with trees, it's something that fills space, and then you're seeing the 2D projection into your eyes. This is a fractal that doesn't fill space. This is frost growing on the window. It's a 2-dimensional fractal, and it looks completely different. You wouldn't be confused, okay, between the case where it's something growing on the surface and something that's in the bulk. Likewise here, what we've done with a critical exponent analysis by similar means, we include the fractal numbers here as well as some other critical exponents. We've ruled out this case. It is not the case that this pattern formation is some pattern that's growing only on the surface like frost growing on a window. This is much more like the tree that's happening deep inside the material, and then we see the intersection of it with the surface. So, yeah, we've ruled out the 2D case. It's a 3D phenomenon. Now, another curious thing that came up here. So we can say that there are 3D critical nematic textures happening in BSCCO. I call them nematic because of the broken rotational symmetry. So a liquid that breaks rotational symmetry is a nematic. So since we're tracking the stripe orientations, we're tracking just the nematic order parameter. So this is a generic phase diagram of cuprate superconductors. Temperature is a function of doping. And what I showed you is inside the superconducting dome, and I showed you the underdoped 32 Kelvin sample. But between them, Jenny and Eric have samples that cover the entire doping range from underdoped to optimally doped to overdoped. And so we did this same analysis on all those different dopings, 5 different dopings. We see the same critical exponents at every doping. That's good. That's consistent with critical behavior. As a function of parameters, the critical exponents should not shift. What should change is the correlation length, like we saw as we went through the demonstration with the test tube. The correlation length grows to infinity at the critical point and then comes back away again. However, what was curious is that we could not detect a change in the correlation length. I was expecting to see that as a function of doping, we would see the correlation length blow up at a particular doping, and that would be the critical doping. But in fact, we just see 2 decades of scaling throughout. It's scaling, it's power law scaling throughout their entire field of view. So what we can say is that the correlation length exceeds their field of view throughout this entire doping range. Now that's also, so these are the different dopings, 2 different underdoped, optimally doped, 2 different overdoped samples. And so that is curious because this is a very large critical region. Okay, so this is not like the case of, say, superfluid helium where you have to get insanely close to the transition to see the criticality. This is very robust, large critical region. So that's a bit curious as well. And it's that broad criticality, the fact that there's critical behavior, power law scaling out to the entire field of view through the entire doping range, that's actually helping us distinguish between the clean case and the random field case. That broad critical region is characteristic of random field models. So you can get 2 decades of scaling even 50% away from the critical point in a random field model. So the random field, the very large critical region of the random field model explains the doping independence that we saw. Now the prediction would be, give us larger fields of view, and then we should be able to detect that correlation length, and that the correlation length should be a function of doping. So I would love to have much larger fields of view. I think we will have to go to a different probe because STM experimentalists don't want to give me, times 100 dynamic range here. Okay, thanks. Also, the static nature of the patterns is closer to random field physics than to the clean Ising model, which would be expected to have some temperature fluctuations. The static nature here indicates, this is the data in the middle. Sorry, this is BSCCO, the data I showed you before. This is a visualization of textures that would come out of a 3D random field Ising model measured at a free surface. So these are simulations out of my group, or a clean 3D Ising model at a free surface. And so the fact that these patterns that are seen in an experiment are static are another indicator that it's random field physics because the barriers to equilibration go sky high in random field models. Rather than the usual critical slowing down, they have extreme critical slowing down. The time scales for equilibration blow up exponentially as you approach the critical point. So, our conclusion here is that BSCCO has 3D critical nematic correlations throughout the superconducting doping range. And there are large barriers to equilibration, inhomogeneity there. This is the fixed point that this pattern formation is near. But moreover, I want to emphasize that this is not a quantum critical point. So what does a quantum critical point look like? Quantum critical point, as a function of some parameter, you're increasing quantum fluctuations, and the critical region is actually pretty narrow. It's confined to, in this case, it would be confined to the critical doping, and come up in a wedge at temperatures above that doping. It's a narrow range. Whereas what we're seeing here is that the data set coming out of Hoffman and Eric's group is critical throughout the doping range. It's not like quantum criticality, but it is like random field criticality, which is a classical zero temperature criticality. It just has a much, much broader critical region. So the critical region here in a random field model is huge. Like I said, you can get 2 decades of scaling within a factor of 2 of the critical point. So I claim that this looks much more like this case. It's not a quantum criticality because it's a very broad critical region. And I will leave you with those ideas, and thank you for your attention.
Thank you very much, Erica. Great. Questions, please. Antonio, and then it will be you.
Thank you for this beautiful talk. I just wonder, in your theoretical model for like physics for ladies, you can interpret your theoretical picture as insulator and metal, blue and red, like insulator and metal.
Right.
It's okay?
Yes.
So if it's this, we have published recently a paper on mercury compound, superconductor, that are the critical point of strain.
Okay.
And doping, and then you have 4 decades of power law.
4 decades, okay,
4
nice.
decades, and now we can go to 6 decades, because now we can do with the X-ray beam, you can go from 10 nanometer to 500 micron. So you can have full decades, so we got 4 decades up to now, at the critical point of strain and doping.
Very nice. Very nice. I will talk to you about that.
There is a lot of work. We go very slow, but...
Yeah, very nice. I mean, we have actually analyzed it for these metal insulator transition materials, for neodymium nickelate and for vanadium dioxide. But I would love to have access to data sets that have more dynamic range.
Yeah. But it's coming.
Very nice.
Okay, so this is more like a comment than a question. I think a percolative transition can be both first order and second order. And essentially what you call a wide critical region is a characteristic of a first order transition, which is always a crossover in the average quantities. And the smoking gun is essentially whether your percolative cluster is staying put on the scale of the experiment, or it is, changing very quickly on the scale of the experiment. Because in a first order transition, the typical situation locally is that when something flips, it flips. And it stays that way. And you need a lot of samples to build up the average behavior at a given point. While in a second order transition, you sit at a given point, this is standard molecular field theory, and you see everything in time happening on that one point, you see. So I think that your results actually point very strongly in the direction that we have a first order phase transition and not a quantum critical point.
Well, okay, so I appreciate the comment. We should talk more about that. So in the models that I used, if I wanted to see the first order behavior, I would drive as a function of applied field. And now let me just put up the Hamiltonian here. So there is a first order phase transition in the model for sure. You would add another term which would be applied field. And so as a function of applied field is where you see the first order nature of the phase transition. And in fact, that's actually relevant to our comparisons to metal insulator domain physics. So when we're looking at metal insulator domain physics, since they're going from fully metal to fully insulating, that is in the first order direction. And so it definitely comes up there. But there is a range in which there is a critical endpoint still. And so there's this range where the critical endpoint comes back and affects the pattern formation in the first order, on the first order line for a little bit near the critical point. So I agree with you. We see that in the metal insulator transition materials. Here, if you wanted to see the first order behavior, I mean, we should talk more. I would love to know more if you think there's true first order behavior in here. But my understanding is that from this model, well, at least theoretically speaking, the way I would get the first order behavior is with an external applied field. And the way you would have an external applied field in this physical system is something that couples to the stripe orientation. So it would need strain. And so we have talked with experimentalists about applying strain. Uniaxial strain in one direction as you cool versus, say, uniaxial strain in the other direction as you field cool, and looking at those differences. And that should be the first order line But we should talk more.
Okay, I agree with that. I'd just like to point out that the question is what you need to do in the model to get what happens in reality. Okay?
Yes.
And,
Yes.
and the question is whether the spanning cluster in real BSCO is sitting there or fluctuating quickly.
Oh yeah, it's static. Now this is at 6 Kelvin.
That's my point. That's my point.
It's 6 Kelvin,
it's
right?
Static.
Well, it's static, but a good reason to expect static here is because the timescales to equilibration have gone through the roof, right? So the timescales, I mean, the random field Ising model is notorious for long equilibration times. This is why permanent magnets stick around, right? You have just an insanely long equilibration time. Yeah.
Okay, please.
So not all of us are lucky to have STM probe, but we can still measure, most of us can measure penetration depth or coherence length as a function of temperature. Can you predict critical exponents?
I will think about that. I will
All
think
right.
about that. The connection we would have to make would be between the coherence length and the coherence length and the penetration depth, right? So we would have to work very hard to put in the superconducting order parameter on top of these textures to make those predictions. It's a very nice idea. Yeah, we haven't gotten there yet. It's a good idea.
Okay, let's, before we thank the speaker,
I can reply
small-
to his question. So the external field is a strain, and that's you have a first order phase transition. And then in order to get the coherence length superconductivity, you have to follow the idea of a Winokur, because you have a superconductor to insulator transition. It's clear, you can see from this way.
So one small comment at this point. Okay,
Yeah, the critical
Okay.
response, they come from, you have to put a superconductivity in a complex metal.
you use this, random field model as a just model, but it's always a question what disorder is doing, because it was an old paper by Alexander Finkelstein, which is classic now, but it looks like nobody ever read it. And what he showed exactly that what disorder is doing is actually to tune the Coulomb interaction. And therefore, disorder has nothing to do with this transition, and this is just the, sort of competition between sort of like Josephson coupling and Coulomb interaction. This is the first. Second, it's just, the comment to this notion.
Okay, so if I understand, your prediction is that if I add the superconducting order parameter on top of this, the superconducting order parameter won't be sensitive to
For
the
example,
disorder.
You tune it with the
Nice.
disorder, but
Yeah.
it's fine. But another point to make is that, as Carla demonstrated a couple of days ago, it was a rigorous calculation of the superconductor to insulator transition. It's first order, and this is quantum critical point, period. The fact that it's first order does not mean that it's not quantum critical point. And what was, again, a rigorous prediction about this is that in the vicinity of this quantum critical point, first order, you do have this self-induced granular structure, exactly what Erica beautifully demonstrated. So everything seems to be quite consistent. Okay, so thank you very much again, and
Thanks. Thank you.
great. Thank you.